Okay, is this live? All right. Oh man, the quality is still not great. Why? What if I change? Okay, if I change the quality to 720p, it's acceptable, barely. So yeah, I think we can get started. So now let me tell the story of this book. Actually, hold on, I'm just waiting for it to reload here now that I've pushed the page down. There's so much latency. Okay, I think this is all right. Yeah. So let me explain what this book is. There's a bunch of. I did some arts and crafts with the pizza boxes, and a bunch of crumbs came out. Anyway. So, oh, that's way too close. Well, anyway, I'll just tell you the title. A Theory of Sample Data Control Systems by Lindorf. Now, about a week ago, or maybe longer than that, I was walking with a friend of mine, and I was saying how I never understood how control systems worked when, well, I kind of don't understand controls that well in the first place, but even less so when it comes to sample data systems. In other words, a very common use case of controls. In fact, if you take a look at the introduction to the book, let me just find it here. The subject of sample data control systems has assumed importance as a direct consequence of the growth and popularity of the digital computer. In other words, we need controls with computers. And computers, they sample data, there is quantization, there is time delay. These are all things that I wish I had understood better in controls, and I just want to point out briefly that this book is from 1965. So, yeah. Now, how did I get this book? Actually, let me show you this. This is something you can see. Today I was at a flea market looking for some other things with a friend of mine, and we were browsing through a bunch of used books in one of the vendors, or at one of the vendors, and most of the books were, there were some kids books, there were some fantasy books and stuff like that, and then at the back there was just a bunch of textbooks. And I saw this one sitting there and I was like, oh, perfect. I have been wanting to learn about sample data control systems. Let me just quickly show this signature here. I definitely interpret this middle initial as an E. This is B, U, probably CH, and then maybe A, Buka. I don't know if that's right. I have no idea what this first letter is, but luckily there is a second signature on the inside cover here. This extra trailing at the end could be an R, so this could be Bucar. And I think that's either a J or an F. It's more likely that it's an F. So I read this as F-E, Buca or Buchar, something like that, Bucher. I have no idea who this person is or how this book came to be at the flea market. Now, I saw this book on the shelf and I was thinking to myself, there's no price written on it, as you can see. And I was thinking to myself, how much would I want to pay for this? And I thought, 25 bucks. It's an old book. It's in good shape and the information is probably quite good. And actually, I looked it up after I got home, and it's quite hard to find, as far as I can see. Well, yeah, I was only willing to pay 25 bucks for it because as much as I want to learn about sample data control systems, it's not my biggest priority in life. So I pick up the book and I find the vendor and I ask him how much he wants for it. And he starts flipping through the book, looking through all the pages, and says like, oh, is this physics? And I'm standing there thinking like, well, I guess it's physics. Technically, everything's physics. And I say, yeah. He says, oh, yeah, this is a very good book. It's very hard to find. And he was right about it being hard to find. I don't know if he knew it was a good book. And he says $50, and I go, I'm not gonna pay $50 for this. I don't want it that bad. And I say, I'm sorry, that's okay. I'll put it back. And he goes, well, okay. Well, could you do $40? And I go, no, it's $25, right? And I should point out, this is the first and only time I have haggled for anything in my life. It's not something I really like to do. And the guy says, "Oh, you know what? Fine. It's hurting me, but because you're a student, and I love you for studying, and I'll give it to you for 25. It's all about studying." He like pats me on the arm, and this was a very bizarre interaction because I have no idea like if this guy. You know what I mean? Like he had hundreds, thousands of books piled up there. I don't think he was making any big losses by selling this book for 25, but I don't know. I have no idea what price he was really trying to get from it, and if I scammed him or if he scammed me or neither. But I thought to myself that I would be willing to pay 25, and so I paid 25 for it. If I assumed this guy was being honest, then his only objective in life is to help me study, and so I have to honor his wishes by studying. So here we are. With that story time over, let's start taking a look. I guess I could take a quick skim here. The aim of Chapter 1 is twofold. The first objective is to provide a description of the sampling process and its identification with practical applications so that tangible associations may be made with the mathematical models to be developed in subsequent chapters. Second is to discuss the feedback concept in terms of the various factors that must be considered in any realistic approach to design. Okay, so Chapter 1 is just fluff. Chapter 2 is an introduction to difference equations in the Z transform. Just as an aside, I did study difference equations in the Z transform in one of my favorite courses of all time. I took DSP with Professor Stevenson, and I learned a lot, but there was a lot of stuff I was still shaky on by the end, and by now I've forgotten quite a few of the finer details. So I'm definitely going to be going through Chapter 2. The pulse transfer function is considered in detail. Actually, hold on. Maybe I should be doing this. The pulse transfer function is considered in detail in anticipation of its effective use as a mathematical model. Mathematical concepts used throughout the book are introduced in relation to the linear pulse filter. Okay, well, we'll skim over that. Chapter 3 is largely concerned with the mathematical relationship between analog transfer functions and the associated pulse model. In this connection, the concept of a transform pair is introduced, and emphasis is placed on the development of general relationships between the transform domains, which assume importance in sampled data theory. The mathematical manipulations, actually it would be better if I did it like this, wouldn't it? The mathematical manipulations in subsequent chapters are thereby substantially simplified. Since the signals within a given system appear in both continuous and discrete form, the development of a mathematical description of the conversion process is required. The sampling theorem enters here. I am quite comfortable with the sampling theorem, or at least I think I am, as a concept of fundamental importance. Finally, attention is directed to the algebra of sample data systems. This topic is conveniently studied with the aid of signal flow graphs. Yeah, okay. So there's that standard form 1, standard form 2 stuff that I kind of got, but I've never really felt like I totally was comfortable with it. In Chapter 4, the classical design parameters such as the velocity, constant damage ratio, and response time. That's sort of oh man, we got root locus. Well, okay, my reaction here is because root locus, I did that in a controls course with another professor who shall go unnamed that I did not particularly learn a lot from. Anyway, root locus and frequency response techniques. Compensation is derived in relation to various objectives. Yeah, okay, so this is where we actually have engineering design. Chapter 5 treats the sensitivity function as a design parameter. It is shown that a limitation is imposed on the sensitivity function. I don't actually know what the sensitivity function is. This limitation can be removed by analog compensation. Design equations are formulated to measure the relative benefits to be obtained from analog and digital compensation. Chapter 6 is concerned with statistical design techniques in which the statistical parameters are derived in relation to the sampled variable. The optimization problem is then solved in terms of the mean square error criterion. Oh, that's neat. Subject to a constraint on the average power to the plant. Actually, I think I need to fix my focus here slightly. 1 second. I have to have this on manual focus or else it'll not work. Focus. That's making it worse. Oh, that's making it much worse. Actually, that was already about as good as it was going to get. For some reason, streaming books is just difficult or something. I don't know. Chapter 7 is introduction to state variables. Yeah, the vector difference equation. The fundamental properties of linear transformations are presented under the assumption that the reader is not necessarily familiar with the geometrical concepts that can be associated with state variables. Okay. Particular attention is given to the method of normalizing the state space coordinates since subsequent design process simplify use of this technique. Okay, we'll look at that. I mean, we're going to look at everything. Maybe not chapter 1 in great detail, but... And then we have the Lyapunov's direct method, which is something I did in nonlinear controls. That's something I did once I got to the master's program. And man, yeah, I really fell behind there. So I've definitely wanted to understand the stuff from nonlinear controls better. Oh, actually, I should try to move this into the center of the... Yeah, okay. Okay, I think I'm done reading this. Yeah, now we have nonlinear. I mean, nonlinear stuff is just a whole other can of worms. So, you know, we'll see how far we get. Yeah, I mean... sampling process occurs the current widespread interests, indirect advantages and result from the introduction of sampling into the system, the inclusion of digital computer. Oh, we got a diagram. Let's look at the diagram. Yeah, so, man, this focus, is there anything I can do to improve this focus? Let me try one more time. You can't see it here, but on my OBS, like, the only thing I can do to adjust the focus is click and drag like a little slider, but it's really, really sensitive to tiny mouse movements. It makes it hard to set it accurately. Let's just try auto for a second, see what it does. Yeah, this is what it does. It just gets stuck oscillating. Don't ask me why. Oh. No, that's actually handy. There's a little pan control. Tilt does nothing. Alright, well, this is the best focus we're going to get, so yeah, sorry. Anyway, so let me see. Yeah, so this is the thing we... I'm looking at the text around it because... okay. So, yeah, whatever, like, okay, this is what I was looking for. Description of a sample data control system. Unfortunately, you see this shadow up here. There's not much I can, actually, maybe I could, oh man, all of this is gonna come crashing down to the floor, probably, if I don't. So if I do this. Oh yeah, actually that did help. Okay, well, it helped a little. Gently, 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 gently. Okay, yeah, I think this is helping. The book is hanging half off the back of the table there, but anyway. Okay, now that I've moved the webcam, let me try one more time to adjust the focus as best I can. This wouldn't be as big of a problem if I had a better webcam, but all right, this is the last time I'm playing with the focus for today. So we have input signal and noise, digital computer, control system, output variable, measuring instruments, instrument noise, discrete data channel, and continuous channel. I actually don't know what this is supposed to be, but yeah, none of this is that deep. Okay, here we go. We have a definition of the sensitivity function. A worthwhile question, which it seems should be answered in the study of feedback systems, is what advantages has feedback to offer over open loop control? What? Are you serious? Everyone knows that. Anyway, it is well known that feedback adds to the complexity and cost of a control system. Well, yeah. Furthermore, it adds to the complexity of the analytical aspects as well. Sometimes no loop configuration may actually be favored. For example, maybe, yeah, okay, everyone knows this. What's the sensitivity function? The sensitivity function introduced by Bode helps to identify the adequacy of feedback in a given situation. Oh, I didn't know that. For the present, a qualitative definition of sensitivity function will suffice. It is defined here as a measure of the change in the transmission characteristics of the system per change in the transmission characteristics of the plant. Ideally, the sensitivity function should be small over the system bandwidth. I don't get it. It is defined here as a measure of the change in the transmission characteristics of the system. For example, the fact that a system may have zero sensitivity at zero frequency offers no assurance that its sensitivity function will not have a magnitude greater than 1 in the critical range of frequencies, which influences the system's design characteristics. It is generally accepted that feedback is useful primarily in reducing the sensitivity of the system to load disturbances and variations in the plant. Interesting. Those factors that limit the attainment of a desired sensitivity function are therefore of great importance to the designer. It will be shown that the sampling process imposes one such limitation. Interesting. The fact must be recognized if the design of sample data is to be realistically formulated. Consider the signal flow graph in figure 1.6. Which is a representation of a linear system with a plant that provides access to one output. System function is defined by, okay, whatever. Where the hell's F? This is what I get for skipping the boring sections. I don't know what their notation is. F, F, F. I think F is just, I think this is how they're defining F. Like F is defined as C over R, the transfer function between the output and the input. I don't know why they bothered to put a 1 on here, but, you know, that's nice. And I don't know exactly what G, P, and H stand for, but this is bringing back some memories looking at these equations. I'm just trying to think in my head. All right, hold on. Let me get some paper here. Hold on. Where's my bookmark? 1 second. All right. Let's see how much controls, like controls 101 I can remember here. So we have a control input, which I guess I'll call I. Oh, no, R is the reference. Okay, we have a reference value, and then we have our subtractor here. This is kind of embarrassing. Somebody who has a master's in engineering should not be struggling to remember like the basic formulation of a control loop. We'll figure it out. We'll figure it out. I'm just rusty, that's all. Also, I don't want to sound like I'm bragging about my master's. I actually don't really think very highly of, or well, that's not true. Like having a master's, like is obviously something I'm really lucky to have been able to do. What I mean to say is it doesn't mean that I'm like smarter or anything or better. It just means that I was lucky. Anyway, what I'm trying to get at here is also I'm writing at such an awkward angle, and I'm trying to clean up the writing as I go. So we have our reference value. I'm really trying hard to keep this diagram looking neat. It goes into the subtractor. What comes out is, I'll call it the error, and this is our control box. You know, our magic goes in here, and then this is our control value, which goes into the plant, and then we have the measurement here, which, if we're lucky, this is an identity function, but you know, it almost never is. Oh my god. Shoot, I think I need to adjust the contrast, or maybe I need to use a darker pencil because this is really hard to read. Oh man. Alright, let me try adjusting the contrast a little bit. The contrast didn't really make much of a difference, but maybe with the handwriting it will. No, that's not the contrast, that's the brightness. And these sliders are really sensitive. I guess I'll just have to make an effort to write like really, really, really clearly and really dark. Oh, sharpness. I just cranked the sharpness up all the way and it helps a lot. Also, it might have helped if I had like if I was using 0.5 millimeter instead of 0.7, but anyway, we have our measurement here. Man, that is still really hard to read. It looks dark for me. What if I try adjusting the white balance? Oh man, no. Okay. Okay, this is about as good as I can do for now. I'll try one more time to make this legible. And it's not that I really care about this particular diagram, it's that I am going to be writing more stuff as I read through this book, and I do want it to be legible, so I need to figure out how to do it. So what if I do that? Man, I don't understand why that's so hard to read. It looks fine to my eyes. Okay, I think I do want to keep the sharpness up there. Where's this line coming from right here? I think the sharpening algorithm is adding artifacts. That's probably what's going on here. It also seems to depend. There is, oh shoot, there's some light reflecting off the graphite in a weird way. Man, this is super annoying. Also, by the way, this doesn't go here. This is the output. That goes in there. Okay. Now, our goal is we want 0 here. Okay, if I write and don't erase and write over the erased paper, it does seem to be fairly legible, so. Alright, we'll leave the settings like this and hope that this works. And I should also, well, I just said I shouldn't write over erased stuff here, but what I mean by magic is actually like our control system. And I think, so let's call this, I don't know, let's call this M for measured. And let's call the plant, I think it's typical to call this F. I know, I should leave that in. Well, let me write it above. I'm pretty sure it's typical to call this F. I'm struggling to remember the usual notation. And we usually call this measurement G, right? Man, I should just look it up. This is all well and good, and it's nice, but Controls 101. Let's look it up, see what we got. Oh, actually, there was those really good Swarthmore College articles that I used to use a lot. Oh, no, it was just a bunch of pages on root locus. Oh, no, never mind. I found it. Well, as I have said a million times when I was streaming other things, I don't really necessarily stream this for people to watch. It's more for my own reference if I want to look at it again in the future. But at the same time, it is handy to, well, it doesn't have to be a live stream, but it is handy to record it. The only reason it's a live stream is because I don't have enough disk space to record them and then upload them. But I think there's some value in making stuff like this public because, if I remember I did something, I can link it to someone, and any sufficiently motivated person can go through and find something that they're looking for. Although I don't make that easy in any way. Anyway, let's just go back here too. And there was that guy who made all those controls videos that I used to use when I was desperately trying to understand my bad controls prof. If I just look up controls, what do I get? There's that guy who did like the Khan Academy style videos. Oh, here it is. Yeah, Brian Douglas. I remember this. Yeah. It's all coming back to me now. Yeah, I got it right. Yeah, I did get it right. Good for me. Now, yeah, okay. So this is, okay, I don't know why I was doubting myself. This is exactly the classical, way of drawing it. And now what I'm trying to remember, I'll use the video if I need to. Now what I'm trying to remember is writing out the transfer function for O relative to what exactly? So we have that O over C equals F. So now let me open, finally, the page of that book. Well, no, this doesn't look the same. There's this U thing. I don't know what U is. Okay, there is something about degrees of freedom. Hold on. Oh yeah, it was just the page before. They don't actually say what they mean by degrees of freedom. So we. Oh, wait. Is this drawing the representation of our control system? Because I noticed they use R for reference and C. Well, I've been calling this C for controlled system. I don't know what U is. C over R is equal to F. Okay, that makes sense to me. And then GP equals 1 plus. It's equal to GP over 1 plus L, where L equals HP is the loop transmission. This is really familiar. That's what I'm trying to remember, where this over 1 plus the loop transmission comes from. So it'll come back to me, I'm sure. So now what they were talking about here is well, if I just ignore their letters, I think what they're actually talking about here is we have O over R is equal to, so the control system, we'll call it S. And the plant is F. And our measurement is G. And we'd be quite happy if G was equal to 1, or at least a scalar. So over R is equal to we have that R minus GO is equal to 0 if everything's okay. Like assuming we were able to solve the control problem and make this work, then we have R minus GO equals 0. And we also have that wait. But if this is 0, then SF times 0 is 0, so O is 0. That can't be right. What am I doing wrong here? I'm just looking it up here in Brian Douglas's video now. These are really good videos, by the way. These saved my butt in that first controls class. Because not only was the professor not effective, shall we say, but he used a textbook which was like the textbook equivalent of, I don't know, of him, honestly. No, no, at least he had some personality. Not only was the textbook confusing, hard to follow, but it was dry as a bone. So yeah, these Brian Douglas videos were a godsend. So you don't assume that E is 0. You just end up with two equations, two unknowns. Yeah, I knew something felt wrong. So R minus GO is equal to E. And then we also have that ESF is equal to O. We're assuming that we know S, we know F. Wait. Yeah, we know S, we know F, we know G, we know R. So we want to get O over R. O is our unknown, and E is also an unknown. Okay, so we have two equations, two unknowns, so we just solve this for O over R. So let's eliminate E. So we can take this, put it in there, and we have loud noise outside. Actually, I don't know if this is still on. Oh shoot! Oh no, it was barely still on camera. Okay, yeah, we got a problem here with the light reflecting. I think if I move this up, man, this is such a bad setup. Maybe if I dim the light a little bit. Okay, that's better actually. I mean, we'll get a shadow, but from I turned on my other light, but okay, so we have R minus GO times SF equals O, and now we just sit and do algebra here. We can take this SF and just, well, you know, this is just one thing. We don't have to treat it as two separate things, but I'll leave it that way. So, yeah, I gotta take it slow. It's been a while. Okay, I'm out of practice. RSF minus SF GO minus O equals 0. No, that wasn't the right move. God, it's also quite late. I'm making excuses. I should stop trying to go fast and be fancy and just do it right. I can do algebra. So we want to O over R. We want to solve for O over R. Okay, now we're getting somewhere. Actually, I could have just left it on this side of the equation. And, well, no, let's leave it here. And so we have man, I cannot believe how rusty I am. Like, this is unbelievable. I haven't done a line of algebra since I don't know. It's literally been years. I don't count the stuff I did yesterday by drawing triangles and writing the equation for a similar triangle, but it's just amazing how little algebra actually comes up in my life despite having spent all that time learning it. Anyway, SF is equal to SF minus 1 over R. Okay. So SF, where did G go? Oh, G is right here. The minus 1 is weird because it is plus 1. Yeah, I did it in my head. See, this is what I mean. I need to stop trying to be fancy here. Okay, just gotta do it right the first time. So you can see my shadow keep popping up here as I like move in front of the light once in a while. So SF equals SF plus 1 O over R. And so finally, our desired quantity over R is SFG. I forgot the G again. Is SF over SFG plus 1. Great. So now we go back in here and try to figure out what the heck they're talking about here. So P is what I was calling SF. For reasons that escape me, they have drawn their measurement as minus h. I have no idea what U is doing, although they don't seem to use it anywhere. And but they have a G on this arrow from R before the subtractor. So for me, that's just 1. Okay. I think I'm on board here. Because if, yeah. You just do the algebra. Okay, so you have 2 equations, 2 unknowns. I still don't know what U is doing, but we have 2 equations, 2 unknowns, and you can solve for C over R. Great. Finally, I can move on. Oh, wait, this is the second half of the sentence. In order to examine the effect of plant parameter variations on the system response, a sensitivity function, which is introduced, which is defined as the sensitivity PF, where F is, okay, I'm starting to understand it here. So F is this C over R, and so change in F over F. Hold on, let me, there's so much, this is such a bad setup, but whatever. Change in F over a change in P over P. What's P again? P is the plant. It's not clear to me where the control system lies in all this, but I don't know. The result this result is of immediate interest in pointing to the fact that the sensitivity function depends on the nominal loop transmission, that the nominal system function can therefore be designed to be independent of the sensitivity by an appropriate choice of G. That the system possessing these properties is said to have 2 degrees of freedom. It is to say 2 transmission paths, in this case F and L, can be established independently of each other. They just dropped this thing out of nowhere, this sensitivity function. Like, they assume that you already know it, I think. Hold on, let me man, I'm trying to make sense of all this. Maybe it was bad to start this at. What time is it? Oh my god, it's midnight. Well, anyway, let's just keep going until we fall asleep. I don't understand what the heck this graph is supposed to be. They just say consider the signal flow graph. This is the first time they use the term signal flow graph, for starters. So they assume we already know what that is. I'm just quickly reading, looking for the explanation of what they mean by a signal graph. Maybe this book isn't good. It seems like it could be okay, but what am I missing here? Like, this C over R is, I guess... Is this just supposed to be an arbitrary graph that has nodes reminiscent of... Oh, I just realized why they put a minus here. It's because this isn't a subtractor. All these nodes are addition nodes. Okay, that makes sense. So... It's strange. They say that the system function is defined by GP over 1 plus L, where L is the loop transmission. And I'm thinking to myself, wait, where did U come from? What is U, like this U up here? What does that mean? Like, what is this? And the system function isn't defined by that. It is that. Like, we're not... I could define it to be 0 if I wanted to make my life easy. There, book over. Everything's 0. Like... Alright, let's just read the text. In order to examine the effect of plant parameter variations... Someone launching fireworks? Hold on, I'm gonna go take a look. Well, anyway, let's keep going. They're trying to define the loop not the loop transmission, the sensitivity function by, I don't know. In order to examine the effect of plant parameter variations on the system response, a sensitivity function is introduced, which is defined as blah. Now, f is a function of p, right? F is equal to GP over 1 plus HP. Why could they just... Man, it's my book. It's so much easier to read like this. It's GP over 1 plus HP, right? F is defined as C over R, which means it's GP over 1 plus HP. So F is a function of P, among other things. By substituting 1.1, that F is equal to this, GP over 1 plus HP. By substituting 1.1 to equation 1.2, it follows that the sensitivity function takes the form 1 over 1 plus L0. I'm writing at such a bad angle. I have no idea what L0 is. I'm just guessing that it's HP0. All right, let's see if we can make sense of how they did that. So, my paper, my clipboard here is falling off the back of the table, but there's nothing I can really do. P is defined as delta, sorry, hold on. It's delta F over F over delta P over P. We define that delta F is equal to F minus F naught, and likewise delta P is equal to P minus P naught. So this SFP is equal to F minus F naught over P minus P naught times P over F, but F is equal to GP over 1 plus HP. So SFP is equal to, we want it in terms of P. Well, what happened to the F naught? Oh, it does. Oh. And F naught is equal to GP naught over 1 plus HP naught. Oh, you can't see that. So SFP well, I mean, let's just plug in and simplify. GP over 1 plus HP minus GP naught over 1 plus HP naught over P minus P naught times P over GP over 1 plus HP. Right? God, what a mess. How can it not depend on P? That just doesn't make sense. How on earth? What? By substituting equation 1.1 into equation 2, it follows that the sensitivity function takes the form blah. I still haven't figured out like why the sensitivity function is defined like this. I'm looking at the next couple lines in the book to see if they explain it at all, but they don't. Okay, we can factor out a G. Oh, the G actually goes away, right? Because we can factor out a G from this first term by doing this. But then that cancels with that. So let's just write that out here. Not that I have any clue what G means in terms of a control system, but let's just keep going. Plus HP minus P naught. Man, I don't know if you could hear that, but someone setting off fireworks in College Park. They're still setting off fireworks. Man, I mean, should I know what the meaning of... Oh, is this Orthodox New Year? No, it couldn't be. I didn't even think... No, Orthodox New Year was last week. What is special about January 21st? What is special about the 22nd? I don't know, I give up. I think it's just people putting on fireworks for no reason. Which is fine. I'm just curious, that's all. All right, let's keep doing the algebra here and seeing where it takes us. I was in the middle of writing this, so P. Oh my god, dude. P over 1 plus HP minus P naught over 1 plus HP naught. All of this divided by P minus P naught times, and let's simplify this fraction here. Wait. Oh, I could have actually got rid of this P over here as well. So actually we just have 1 plus HP. So let's just do this. P minus 1 plus HP over 1 plus H P naught times P naught over P minus P naught. I'm trying to see how to simplify this. Let's just put it quickly into Wolfram and see what it gives us. Just to make sure I, am doing something right. Wolfram alpha. Come on, Wolfram, you can do this. Oh, wow, it does actually simplify to the expression that they give. So yeah, I guess I haven't made any mistakes yet. So how would I simplify that? Wolfram alpha can do it, I can do it. Oh, wait a second. Oh, no. Is this... in my mind, I'm trying different things to see what takes me closer to the finish line. So if I divide the top and bottom by p, that becomes 1, that becomes 1. But then this just doesn't do anything. And then this becomes p naught over p, so that doesn't seem helpful. If I multiply the top and bottom by p plus p naught, nah, that's ridiculous. If I separate this into two fractions, then maybe I'll see something if I do that. So p over p minus p naught minus 1 plus hp for 1 plus hp naught minus p naught over p minus p naught. Oh, wait a sec. No, I don't see it. I don't see how they simplified it any further. Let me try something else. Now if I expand out the top, oh, we have p plus hp naught p, and then over here we have minus hp naught p. Oh, right. So it is as I multiplied the top and bottom of this fraction, let me write it in here, times, I multiply the top and bottom of this fraction by 1 plus hp naught. Alright, now I see it. Whew, that was a tough one. Well, tough for somebody who's out of practice. And what you can see is we have hp naught p with a minus sign, then hp naught p with a plus sign. So all we're left with up here is just p minus p naught. So the p minus p naughts go away. Finally, we get 1 over 1 plus hp naught. Okay. Okay, we made it to the finish line. Now I can read the next line of the book. The whole book is going to be like this, by the way. Hope you're ready. I still don't know what motivated this definition. The result is of immediate interest in pointing to the fact that the sensitivity function depends on the nominal loop transmission, and that the nominal system function f can therefore be designed to be independent of the sensitivity by an appropriate choice of g. What does that mean? What? Let me read that sentence again. the nominal system function f naught. Oh, f naught is not a constant. Is f naught a whole function? Man, this is a very bizarre notation. So if f naught is the nominal system function, and p naught is the nominal plant function, and then f is some proposed new function, man, this would have been a lot easier if, or maybe not easier, but it would have been a better hint if A, they had told me what domain each of these variables belongs to. Well, no, I see. That doesn't help because the f and p are up here. I guess I should have been able to figure out that f naught and p naught were not scalars, but... Well, I mean, okay, they are. And like, as in this linear graph, they actually do happen to be scalars. So, fine. But now we're asking the question, so the sensitivity function doesn't depend, it only depends on the plant and h? By an appropriate choice of g? Oh, the role of the sensitivity function is going to become apparent, guys. I hope you're ready. This setup is so precarious. I'm going to have to make a more permanent setup. Maybe I'll hot glue this together instead of just having it balanced. So if we set f to 0, and what? If u is taken to represent the disturbance response? What? Dude, what is... Okay, hold on. Let me see if they explain the meaning of disturbance response. Oh, okay. I think if I do a little bit of inference here, so when they draw their control, like their plant, they have this thing up here called load disturbance. And they don't actually use the term disturbance in the description of the plant. But what they do say in the last paragraph of that section there is, ignorance of the plant parameters is another factor that must be included with the scope of the design problem. The parameters may vary because of operating conditions, agents, or manufacturing tolerances. In other words, that U is supposed to model, a change over time of the plant. And they don't call it a disturbance in this paragraph. Man, like, is it just me, or is this book bad? Like, am I wrong for thinking that? Like, they just drop all these letters in and draw this diagram, and like expect you to figure out that that's the control loop. And even so, it's like, well, hold it a minute, because like, what is this G and what is this U? Maybe this is obvious for people who have taken controls with the exact terminology and conventions that they used, but all right, let's try reading again how this sensitivity function becomes the role, how its role becomes apparent. The sensitivity function is also useful in measuring the effect of feedback and desensitizing the system to load disturbances. From figure 1.6, it is seen that the disturbance response is given by blah. If U is taken to represent the disturbance response in the absence of feedback, then by identification of equation 3 with equation 1.4, the role of sensitivity function becomes apparent. There are now the signal flow graph represented in figure 1.7, which for some reason now G is after the subtractor, but we're directly subtracting U. I don't exactly know what's going on here. Then they'd write down some equations, and they say it is apparent now that F naught and SPF, wait, what? Have I been writing that? Oh, I've been writing it down wrong. Okay, whoops. Can no longer be controlled independently, such as 1 degree of freedom was not used to its fullest advantage. Any system configuration that can be expressed in the form of the flow graph in figure 1.6 is defined as 2 degree of freedom system. The degree of freedom concept is important in that it identifies a fundamental property of a feedback structure. In order to enlarge the degrees of freedom beyond 2, it is necessary to gain access to more outputs of the plant. Horowitz has suggested that multi-loop systems be defined as those that possess 3 or more degrees of freedom. By adopting Horowitz, hey, this is the guy that wrote that terrible textbook I was telling you about. Or at least somebody with the name Horowitz. The one that incredibly dry, very difficult to follow, full of like the textbook problems, like our prof, like the mark of any bad prof. Or to put it this way, a lot of bad profs just assign textbook problems as homework and then are like, whatever. Well, the textbook problems in this book were just like, or maybe the ones that my prof decided to assign were just like, I don't know how to explain, like, there were these huge problems. Like, I don't mind doing a bigger problem, obviously, on a homework, but like every problem he assigned was like, I don't know how to explain it. Anyway, I'm gonna stop complaining about that controls course. So just keep in mind that I never understood controls properly, even though I've always wanted to. Okay. So I'm a little iffy on what the concept of 2 degrees of freedom is about, and this sensitivity function is just totally baffling. Like, what is that? I just don't get it. And someone's talking about having multiple loops, and now here's a frequency response plot. Like, Based on further sensitivity function. Okay, I guess the figure 1.9 is described on the next page. Sensitivity function is small enough over the system bandwidth it is permissible to assume that f naught is equal to g1. Man, like, am I even supposed to understand this? Like, I'm totally lost. Totally lost. Let me just browse through here. Come on. Oh, it's just one page. Man, this isn't a... This is just a completely unhelpful introduction. Like, none of this makes any sense. It's like, it's not an introduction, it's a summary. Alright. Let's give chapter 2 a shot. I'm definitely feeling tired, but let's try this. This chapter is fundamentally concerned with the study of linear difference equations with constant coefficients, or LCCDEs as we knew them, and the application of the Laplace transformation as a tool for simplifying their solution. This, at least, is now back on solid ground. I mean, I haven't touched it in a while, but Dr. Stevenson was awesome. One of the best profs I ever had, if not the best. Yeah, anyway. Since these mathematical concepts will prove to be the foundation for subsequent discussion of sample data systems, this material should be viewed as a necessary background for further development of the subject. Okay. Like, why did you even have to write that? We're in chapter 2 of your book. Like, anyway, I'm gonna stop complaining. I'm distracting myself because I'm tired, but let's force ourselves through. It is by associating the physical system with a pulse model, which is governed by difference equations, that a workable mathematical base is established. Therefore, much attention in the ensuing chapters will be devoted to the means of generating the pulse model and ensuring that it constitutes an adequate representation of the system. For the present, however, our concern is directed to the study of the pulse filter per se, with the purpose of showing how the techniques of analysis, which are so important in the realm of continuous systems, are applicable as well to the pulse model. For example, the application of the Routh-Rohlquist method, the Bode diagram, and various stability criteria are to be investigated. Although the pulse filter is to be used as a model of the physical system, it will also assume importance as a means of describing the dynamic characteristics of a digital computer, which may be associated with the control system. Such a digital controller can be described quite naturally in terms of a pulse filter model, since the digital computation is intrinsically related to the difference equation. I mean, I could have guessed that. It may be inferred from these comments that a digital component can in fact be employed to advantage in compensating. This is an odd sentence. Can be employed to advantage in compensating a sample data system. It is fitting, therefore, that the conditions for physical realizability of the pulse filter should also be determined. Okay, this is the first requirement for understanding the concept of the pulse filter is a familiarity with difference equations. The following subject is intended to serve as a brief but sufficient introduction to the subject. Well, I'll be the judge of that. The notion of the first difference is as fundamental to the difference equation as the derivative is to the differential equation. It will be seen that the first difference can be defined in either of two ways, since both definitions find common usage. It's conventional to refer to a backwards as well as a forward difference. These terms are now defined with respect to the function f of t, plotted in figure 2.1. If, as indicated, the sample points are spaced periodically in time, then the function f of nt becomes a numerical sequence for successive values of nt as shown. The first backward difference is now defined as, yeah, okay, fine. It will be observed that if f of nt relates to a real-time function, the forward difference is unrealizable. Yeah, okay, duh. Since it presumes a knowledge of the future, the forward difference, however, will prove to be useful as a theoretical concept, whatever you say. Higher order differences are obtained by repeated application of equation 2.1 or 2.2. The nth difference being denoted by either blah or blah. Oh, we got a footnote. Oh, yeah. You see here, a better notation is with the square brackets. That's what Dr. Stevenson used to do, and that was really nice. So I'll probably, anyway. For example, the second backward difference is written explicitly as this. The second difference of f of n is the first difference of f of n minus f of n minus 1. Okay, none of this is that deep. Following examples serve to illustrate two practical applications of linear difference equations. In these examples, use is made of the two simplest rules for numerical integration. In a later section, these same equations, when related to the transform domain, are used to illustrate the concept of a pulse transfer function. Digital computer and executing according to prescribed instructions the process of addition, multiplication, and data storage. It is capable of representing a linear difference equation. Man, this is such a tedious chapter so far. For instance, the particular process of rectangular integration, which is the simplest rule for numerical integration, describable by a first order difference equation. Thus, if R of n denotes the input data and C of nt denotes the output data, then the rectangular integration rule requires that each successive output be computed according to the relationship. Yeah, fine. Okay. If the first difference defined in equation 2.1 is substituted into equation 2.4, then the difference equation which governs the rectangular integration rule becomes blah. I don't care. This rule is graphically illustrated in figure 2.2a. I also don't care. Trapezoidal integration. I don't care. Impulse modulation. Signal sampling so far has been considered as an operation that converts a continuous function into a numerical sequence. This process can be described in mathematical terms familiar to the engineer by considering the samples of R of t to be represented by a train of impulses in which the amplitude of the impulse occurring at t equals nt is equal to R of nt. The impulse modulation process so described is diagrammatically represented in figure 2.3. Yes, this is ideal sampling, as it's known. None of this is that deep. Man, there's so many fireworks going on today. I wish I knew why. The conditions under which this mathematical form represents a good the physical sampling process are deferred until chapter 3. Okay. For the present, impulse modulation, in other words, ideal sampling, this is what people call If R star of S is used to denote the Laplace transform of R star of t, it follows that. Now I am really gonna struggle to remember, but this is an easy integral to do, at least. It just becomes a discrete sum of the complex, well, I guess S is a complex variable, so what the heck? They use epsilon as E? Good God. Was that something people did in the 1960s? Yeah, so now they're just describing the Z transform as a change of variable, where Z is a complex number. let's keep going. I was just getting text messages. Um, as a general rule, I don't tend to answer text messages after 10 o'clock. Not because I'm liable of losing my temper, but because I basically will just have to go back the next morning and clarify something, and now I send 2 texts instead of 1, and whoever's on the other end, like, they can't use the information until tomorrow anyway, so I'll just answer it when I get up tomorrow. Got marks all over my kitchen counter from my pencil. Anyway, becomes blah. It should be noted that A of delta t minus t is an impulse of amplitude. Yeah, I know that. The term amplitude here. Oh, okay. They're just being mathematically more rigorous. This isn't that rigorous, but It is conventional to omit the star notation on R star of Z as a matter of convenience, the understanding being that R of Z by itself signifies a transformed impulse modulated function. And there is ambiguity, however, the star notation will be used. For example, we shall occasionally have reason to refer to R star as whatever. If star notation is needed, it's RS will be ambiguous. Yep, no problem. Equation 2.10 then defines the Z transform of R of t to be written as script Z of R of t or script Z of R of nt. Yeah, fine. In chapter 3, the Z transform is defined on a more rigorous basis by the complex convolution integral. Ooh, that's interesting. There it will be seen if R of t is Laplace transformable, its Z transform exists. Okay. Z transform of difference equations. Yeah, I've seen all this before. In applying Z transform difference equations, the problem consists essentially of finding the Z transform of time-shifted functions. Consider, for example, the Z transform of the first backwards difference, which is denoted by blah. It will be seen as the right-hand term. This equation can be derived directly by applying the shift theorem. Yeah, and this is all stuff I've seen before. So I'm going to skim it. Sorry to the viewers who don't understand Z transforms. Or I guess I should say sorry to those who aren't lucky enough to have Dr. Stevenson teach it to them. The shift theorem must now be re-examined in relation to the time advanced function, blah, to account for the fact that f of n may be non-zero at n equals 0. The resulting statement of the shift theorem becomes... Oh, I should read this a little more carefully. Sorry. Okay. I do remember seeing this. I'm just trying to remember where that comes from. Oh, yeah. Hmm. Hmm. I forget this. Hold on, let me think about it in my head here for a second. Well, I mean, I have been doing that, but so I think I have no choice but to just actually do out the derivation of the shift theorem. Let's take a quick look at that one more time. Oh, now why did they make this a footnote? The shift theorem as applied to a time delayed function can be derived as follows. Given f of n and its z transform f of z, the transform of f of n minus 1 becomes blah equals blah, and then by choosing change the variable m, yeah, this is exactly what you would do. Now if f of n equals 0 for n less than 0, the lower limit can be changed to, yeah, so you have to change the limits on the summation. Yeah. Okay, now I get it. Okay, now we're good. Okay, pulse transfer function. This is new stuff for me now, maybe. With the tools that have been developed in the preceding sections, it is not possible to introduce the concept of a transfer function d of z, which describes the transmission characteristics of a linear pulse filter. By example, a transfer function will be derived first from the difference equation describing the trapezoidal rule of integration. Okay, in section 2.8, this function is defined more formally by the convolution summation. Wait, this is not very deep. This is just a transfer function. I kind of don't care about this. An enlightening physical representation of equation 2.1, it can be gained from the schematic representation in figure 2.4, which shows one possible development of equation 2.18 in terms of signal channels composed of elemental delay units. Okay. Okay, fine. This power series, by the way, you get it if you, because the final expression is going to be like 1 over 1 plus something, and you can do a power series of 1 over x to get this. Yeah. Man, I'm almost out of steam. I think I better stop. I'm a little disappointed, honestly. This book is getting better in chapter 2 for sure, actually. I haven't had a problem in chapter 2 where something wasn't defined. I did kind of spend a lot of time poking around looking for this footnote, but that's okay. That's just me not paying attention. Yeah, chapter 1 was just a trash fire. Chapter 2 is actually pretty good. And so far this is all stuff I've seen before, although I am refreshing my memory, which is nice. I mean, I definitely would not have been able to sit down and figure this out quickly. It would have taken me a lot of time. And then what else do we have in chapter 2? I'm just going to flip through here quickly. They talk about frequency response, which you get by plugging z equals something. I forget what you plug in, but you plug something in for z, and you can evaluate the z transform on the unit circle. Apparently there's some little methods. Oh, that's neat. Yeah, remember this is in the 1960s, so there's like some methods for like by hand plotting the responses, which is kind of neat. They talk about deconvolution with long division. They talk about stability criterion with reference to the W plane. I know what it is. Oh, that's not W, that's omega. Never mind, okay. And now all of a sudden we talk about Nyquist criterion, right after talking about stability for a while. Never mind, sorry. Yeah, Nyquist criterion, not Nyquist rate. Yeah, the Nyquist criterion, I remember now. It's something to do with the, the circulation integral. Or not oh, hey! Whoa! Check this out. The author left us a little note. Multiply both sides by t for... Hold on, I gotta pull this close to my face to see it. Oh, equivalence? No. Yeah, it does say equivalence. For equivalence of integral from 0 to infinity of e to the tau dt. This must have been something that they were looking at outside this book. I am actually... Oh, dude, look, more handwritten notes. See also page 84. Oh, dude, I love finding other people's handwritten notes in books, when they're good anyway, and I've never found bad ones. I mean, I could leave bad ones. This is getting interesting. Alright, okay, alright. And I think this book is worth a second chance here. We'll keep reading through chapter 2. We've still got quite a ways to go to get out of chapter 2. A good 25 pages. But yeah, I think we should be okay. Now, this is such a bizarre like hodgepodge of like different courses I've taken, or like, how do I put this? The way that when I did this material in school, the way that it was divided into separate courses with their own order of teaching things is completely different. Like, this is just, I recognize stuff from the DSP course, and then stuff from the signals course, and then stuff from my crappy controls course, and it's just like all in a jumble from my point of view. I actually think it's okay, but